Modern vision language models rely on a specific mechanism to process image contexts and output spatial coordinates. They locate objects by generating a sequence of text. This relies on the standard generative paradigm known as next token prediction. In this model, coordinates are emitted one by one, generated sequentially like reading a text string. The bottom section highlights how coordinates are typically handled. In textual digit decoding, the model forces coupled 2D parameters, like the corners of a bounding box, into a serialized 1D token stream. Generating one box requires 21 separate steps, creating a severe latency bottleneck. The problem extends beyond speed. By stretching a single geometric object across multiple sequential tokens, the model loses the structural relationship between those coordinates. A physical object exists all at once, not as a disjointed string of numbers. As long as models rely on 1D token serialization to define 2D shapes, grounding latency remains tied to the number of tokens generated, rather than the scene's complexity. To bypass this limitation, researchers developed the LocateAnything framework. It acts as a structural solution to the sequential inference bottleneck. The core mechanism is parallel box decoding, or PBD. Instead of emitting tokens one by one, PBD groups the entire set of coordinates into a single atomic block. Because the model processes the entire block simultaneously, decoding throughput increases by up to 2.5 times, while simultaneously improving localization quality. Solving this bottleneck involves aligning the model's token structure with the geometry of identified objects. Accelerating generation in standard language models often relies on multi-token prediction, or MTP. Standard MTP trains the model by selecting random positions in a sequence and teaching it to predict arbitrary spans of tokens in parallel. This figure illustrates standard MTP applied to spatial data. In the generic multi-token prediction column, specifically the unstructured sequences, arbitrary chunking breaks spatial boundaries. The model is forced to group geometric coordinates with unrelated semantic class tokens, like the word cat. This forces the model to memorize unreliable overlapping patterns. It induces spurious correlations and amplifies error propagation throughout the sequence. Applying structure-agnostic parallel generation to tightly coupled geometric units destroys spatial coherence and reduces the reliability of the output. Parallel box decoding acts as the architectural remedy by aligning these prediction blocks with structural reality. The absolute rule of PBD is that a complete bounding box, all four corners, must be treated as a single indivisible atomic unit during prediction. This diagram shows the structured block generation process, which enforces a constant constraint. Every functional block is exactly 6 tokens long. In the yellow box block row, notice the anatomy. 2 structural tags at the beginning and end wrap exactly 4 coordinate tokens. If a functional block requires fewer than 6 tokens, the system uses null padding to fill the gaps. This guarantees uniform tensor shapes across all block types. This rigid box-aligned formatting is the structural prerequisite that enables parallel spatial generation without inducing hallucination. Generating these blocks in parallel creates a specific challenge. It can disrupt the causal reasoning logic that standard language decoders rely on. The solution is a dual formulation training strategy. The system concatenates a standard next token prediction sequence with the new blockwise multi-token sequence during training. To prevent data from leaking between these two streams, the architecture relies on a specialized attention mask that governs information flow in 3 distinct ways. The first flow is causal attention. The next token stream operates exactly like a standard language model, strictly attending only to preceding tokens. The second flow is cross-block causal attention. The parallel blocks can see the context of previously generated blocks, but they remain completely blind to any future blocks. The third flow is bidirectional intra-block attention. Inside a single atomic block, all 6 tokens communicate with each other simultaneously, resolving their internal relationships. This tri-layered mask design allows LocateAnything to learn complex structural parameters concurrently, without sacrificing its foundational language logic. During inference, even with perfectly aligned blocks, parallel decoding faces an exploration-exploitation dilemma in visually dense scenes. The first failure mode is format irregularity. When the model struggles at the boundary between two different object categories, it can produce malformed syntax, incorrectly mixing structural tags with coordinate numbers. The second failure mode is spatial ambiguity. When objects are densely packed into regular grids, like rows of parked cars, the parallel output can blur spatial boundaries and generate an intermediate coordinate between two distinct objects. To maintain precision, the system continuously monitors both the syntactic integrity of the string and the mathematical confidence of its coordinates during parallel generation. A robust system requires a dynamic mechanism to detect these specific visual uncertainties and immediately revert to a more stable decoding state. That safeguard is the hybrid decoding policy. It employs high-speed multi-token prediction by default, but seamlessly switches processing modes on demand. The system triggers a fallback if the top coordinate probability drops below an acceptable threshold, or if it detects a formatting violation. This schematic shows the corrected NTP redecoding process. When a trigger is hit, the compromised parallel block is discarded, and the model reverts to standard next token prediction for that specific segment. Notice how the red wrong parallel blocks are replaced. The model auto-regressively decodes only the problematic block in blue, generating it token by token. Once that sequence is completed, it switches right back to high-throughput parallel decoding. This localized correction preserves the vast majority of the speed gains associated with parallel processing, while maintaining the reliability of traditional sequential decoding. By aligning token architectures with geometric reality and gracefully deferring to sequential logic only when visual certainty drops, LocateAnything successfully shifts the speed-accuracy frontier.